very sharply. You want it more complex? Why not? Look at this. You see a diffraction band, our friend. The peak is very intense. It's 260 kilocounts, so this is really the background. There's this narrow peak here. It's single phase. It's not two phases. There's narrow one, broad one, very peaky peaks. And there's this strange feature here. Then you would not say it's a peak. And if you look at that in logarithm scale, you can even say it's even worse. In this case, what can we do? We cannot do what we have done so far. We cannot decouple structure and microstructure. So we really need to work with them together. And unfortunately, if you plug this one into a Rietveld code or a traditional method for structural determination, you don't get anything out of that. Because all those features are related from the fact that microstructure is playing with structure. So you cannot extract one if you do not know the other. You can get a local information on the structure, maybe using other techniques. Or you can get an average idea of the structure using other techniques. But then you need to work out what is the local arrangement of the blocks that are inside your material and how they contribute to the diffraction pattern. Another tool I give you, and just a hint, maybe I can show you today during the workshop, something about that, is what we can do. We need to move from a traditional Rietveld-based approach where we get a 3D periodic lattice that can cope only with periodic defects, and we need to reduce the symmetry. A first possible reduction is to reduce it to 2D. A better one would be to reduce it to 1D, but at least 2D can already open a whole new world. You can still get a 3D periodic case, but you can also get non-periodic defect, not aperiodic structure, but non-periodic. So interlayer system, disordered system, without the one that aperiodic people like to see, so extra satellite peak that tells us that the periodicity of our defect is constant. And you can also have modular system and layer disorder. Actually, you could also get to modulated structures when you got the beautiful peaks. And it's simply a regular stacking of this 2D object. Of course, you need to get building blocks, and you need to get local to have a single unit cell for which you build your complex structure. You need a method to assemble building blocks, so to take our layers and to assemble them. And there's this nice method of traced and coworkers where you see the crystal in a recursive way. So you start with one layer, and you consider the crystals made as one layer plus a crystal self-similar, so a Markov chain type approach. You can work out the intensity for the whole stack. And once you got the intensity, you can have something that works out the powder pattern for you from the intensity of the stacking. And Diffax Plus is the software that, starting from the idea of Diffax, gets to refinement of all the parameters that lead to that stacking. A couple just of things. The first thing is that the calculation is done by integrating in reciprocal space. We need to get in between the black spots, because the information is there. That's why we don't see it using the Rietveld. And that's why it takes time to do this type of calculation. But it comes with some very high flexibility. You can stack whatever you like on top of whatever else you like, any type of stacking, with any direction, any interconnection between the cells. And of course, when you interconnect that, you can have also a probabilistic description of what you are linking. So your crystal is not anymore something deterministic, but is something probabilistic. And it is what changes the world between traditional crystallography, 3D periodic lattice, and structure plus microstructure. You have a probability that the blocks are stacked one on top of the other. The more the number of blocks, the larger the probability matrix. And this is something you can work out. because the information is all in your data. If you got information in the reciprocal space, it's easy. But you can also try to work it out from powders. And just two last slides. The first one is, remember that you need just an extra tool if you cannot use whatever else you got. So if you do not have this problem, do not try using complex tools. Stick to the Rietveld. And remember this stuff here. Software is always a garbage in, garbage out system, unfortunately. Sometimes it's also physics in, physics out. And those are the two last slides. This is a case of a perovskite. If you model it using the Rietveld or traditional methods, you see these red black spots. It is a perovskite. What is wrong with the perovskite? Why do I get this forest of peaks? Because unfortunately, the perovskite stacks in two different fashions, an eye-centered and a primitive. So what happens is that inside our specimen, we got both together. And they are stacked like that, in a statistical way. And the only way to get the right answer using Rietveld is to use the supercell approach. With these 10,000 atoms, fortunately, Topaz is able to work them out in a reasonable time, and you get a match with the final pattern. And this is just described using a probability matrix of transition from one type of stacking to the other type of stacking. So if you want to know more, just contact me. I'll be more than happy to give you all the details and all the software that can help you get into some physics out of the broadening of your peaks. That's it. Remember this, especially for the youngest. Place questions and try to take your ideas out, because usually something good can come out of that Yaroslav already.
Well, thank you very much for that wonderful stepwise, increasingly complex, but wonderfully clear description of how things have moved on. I'm sure there must be plenty of questions.
With all you said, I would like to know your opinion about the PDF. Isn't it an oversimplification as well to the
PDF
material?
approach?
Sorry?
You mean the PDF approach?
Yeah, PDF approach.
Can we talk it after the talk of Simon? I will show you something today.
Okay.
So we can try to make a couple of slides of comparison of the different approaches. So there's a lot of debate on what is the best tool to do what. And there could be different opinions. So better if you talk later, so you also the other people will see the PDF approach, and also the Debye approach, and also the alternative approach that Tomasz will also show, and we can discuss today. I think it's a good point to compare the methods.
I'm looking for young people. Remember that incentive?
The young guy.
Yes, unfortunately, I'm not entitled to 500 euros. Oh, anyhow, I spend a lot of my life with sheet silicates. And if you measure them, the patterns are mostly governed by preferred orientation in many cases. So now you try to analyze a pattern, even on such a simple silicate like kaolinite, and try to get some info from your probabilistic approach. How much is this influenced by the factor like preferred orientation? Mm-hmm. But yes, of course, the possible answer is you use capillary, but of course it only minimizes the influence.
I got two possible answers. The first one is try to limit it as much as you can. And changing your instrumental setup could be a good possibility. The other one is try to live with that if the level of preferred orientation is low. Otherwise, if the level of preferred orientation is massive, then change your tools. That's the only way. You can change your specimen if you can. You can change your data if your instrument allows that. Otherwise, change your tool. If you really want to get something the only possible alternative is to start with the atomic position and build it from the bottom. There's no other option. But at least you can get still some viable information if the preferred orientation is reasonable. You don't get much wrong the stacking sequence, usually. It is the one that is less influenced by the stacking. Of course, you can also play tricks. You start exfoliating it, and you start playing with that. But it's really tricks in the end. You need to put, your brain is really 90% there, your data is 5% probably, and your specimen is even less in this case.
Okay, question from the back. Remember to introduce yourself and where you're from.
Leszek Kowski, Polish Academy of Science. I have a question. If you try this method, let's say at the border of being amorphous, when the grain size is less than 3 nanometers, 2 nanometers.
What do you mean by amorphous?
Yeah, that's the question.
The point is that 3 nanometers, if you're able to, okay, let's put it that way. If you're able to determine that your system is crystalline on the 3 nanometers, and it's easy to do it, if it is amorphous, at a certain point it will crystallize, hopefully. If it is not, then it is already crystalline and will grow. Or you will see what happens. But if you assume that your material is nanocrystalline, then you can extract information. If you already assume that your material is amorphous, then you cannot get anything out of that. Unfortunately, this is based on the assumption that all is crystalline, because everything is worked out in the crystalline regime.
Right at the very back. Yep.
Hi, I'm Carlos from Brazil, and thanks for your lecture. It's very interesting, and that is something that I would wonder to apply in my problems. And I would like to know if you have some clues or something to extract from your data, from the X-ray data, about the boundaries, the interfacial component, or if you are put these effects of the boundaries on the average data, that the results that you have.
Amorphous or not amorphous?
Nanocrystalline.
You got already the answer yourself. For the non-crystalline, use the right tools. It's always like that. If you want to analyze a crystalline material, use the tool for the crystalline. If you want to analyze something that is non-crystalline, then switch to something like the PDF, where the non-crystalline part comes out beautifully. So it's just a matter of really using the right tool for the right problem.
Okay, we have time for 2 very, very brief questions.
Very brief. I'm Matteo from the University of Bologna. If you have, imagine that you have some planar complexes like, I don't know, maybe platinum complexes, planar. Is it possible to model defects in stacking between metals?
Platinum seems one of the most interesting things around, because most people work on that. It's possible, of course. You just need to work out. The problem is that what I've shown you is the infrastructure. In the end, what you then need, you need to put some numbers inside the models. And to calculate some of the defects and quantify some of the defects, you need to know already something, or to work out something like what are the possible stacking sequences, what are the possible reasonable type of defects that you got inside. Remember that this is just a tool that allows you to do the passage from the physical model to the pattern. It's not something that gives you the answer.
Okay, I'm afraid we need to draw a line under it, just in the interest of keeping to time, so I'd ask you all to thank our speaker once again.